Black holes. Just the name evokes a sense of mystery and awe. These celestial objects are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are the ultimate cosmic abysses, where the laws of physics as we know them break down. Black holes challenge our understanding of the universe. They push the boundaries of our scientific knowledge and ignite our imagination. Despite decades of study, they remain one of the most intriguing enigmas in astrophysics. The concept of black holes arises from Einstein's theory of general relativity. This theory describes gravity as the curvature of space-time caused by mass and energy. Imagine a bowling ball placed on a trampoline causing a dip in the fabric. Similarly, massive objects warp the fabric of space-time, creating gravitational wells. Black holes represent the most extreme case of this warping, where space-time is curved infinitely, creating a bottomless pit in the cosmic landscape. To understand black holes, we must first understand the life cycle of stars. Stars are born from collapsing clouds of gas and dust, primarily hydrogen. The immense pressure at their core ignites nuclear fusion, where hydrogen atoms fuse to form helium, releasing tremendous energy. This energy counteracts the inward pull of gravity, creating a delicate balance that allows stars to shine for millions or even billions of years. However, this balance is temporary. As stars age, they consume their hydrogen fuel. Eventually, the core runs out of hydrogen, and the star begins to fuse heavier elements like helium and carbon. This process releases less energy, and the star's core begins to contract under its own gravity. The fate of a star depends on its initial mass. Stars like our Sun will eventually shed their outer layers, leaving behind a dense core called a white dwarf. But for stars much more massive than the Sun, the story takes a dramatic turn, leading to the formation of a black hole. When a massive star exhausts its nuclear fuel, it can no longer support its own weight. The core collapses in on itself, and this collapse can trigger a supernova explosion, one of the most violent events in the universe. During a supernova, the star's outer layers are blasted into space, while the core continues to collapse under its own gravity. If the core is massive enough, gravity will overwhelm all other forces and the collapse will continue indefinitely. As the core collapses, its density and gravity increase without limit. Eventually, the core becomes so dense and its gravitational pull so strong that not even light can escape its grasp. At this point, a black hole is born. The formation of a black hole marks a point of no return. Once an object crosses the boundary beyond which escape is impossible, it is forever trapped within the black hole's gravitational grip. Imagine a vast dark sphere in space. This sphere represents the event horizon of a black hole, the boundary beyond which nothing can return. The event horizon is not a physical surface, but rather a region of space-time where gravity is so strong that even light is bent back on itself. The size of the event horizon is determined by the mass of the black hole. The more massive the black hole, the larger its event horizon. For example, a black hole with the mass of our Sun would have an event horizon with a radius of only about 3 kilometers. If you were to fall into a black hole, you would initially not notice anything unusual as you crossed the event horizon. However, as you fell deeper into the black hole, you would experience increasingly strong gravitational forces. These forces would stretch and squeeze you in a process known as spaghettification. Eventually, you would be torn apart by the extreme tidal forces near the black hole's singularity. Section 5. Singularity, where physics breaks down. At the very center of a black hole lies the singularity, a point of infinite density where all the matter that falls into the black hole is concentrated. Our current understanding of physics breaks down at the singularity. The singularity is often described as a point of zero volume and infinite density. However, it is important to remember that these are mathematical concepts, and their physical meaning at the singularity is not fully understood. Some theories suggest that the singularity may not be a point at all, but rather a ring or some other exotic object. However, without a complete theory of quantum gravity, it is impossible to say for sure what happens at the singularity. Despite our limited understanding, the singularity remains a captivating concept. It represents the ultimate limit of our knowledge and a place where the fundamental nature of space, time, and matter is pushed to its extremes. Section 6. Time dilation, time warps near black holes. One of the most mind-bending aspects of black holes is their effect on time. According to Einstein's theory of general relativity, gravity warps not only space but also time. The stronger the gravity, the slower time runs. Near a black hole, where gravity is incredibly strong, this effect becomes extreme. Imagine two clocks, one far away from a black hole and one near the event horizon. The clock near the black hole would tick much slower than the clock far away. This phenomenon is known as gravitational time dilation. It means that time passes more slowly for objects closer to a black hole than for objects farther away. If you were to observe someone falling into a black hole, you would see their clock slow down as they approach the event horizon. From the perspective of the person falling in, however, time would appear to pass normally. They would cross the event horizon and approach the singularity without experiencing any slowing of time. Section 7. Spaghettification, stretching towards oblivion. As if time dilation wasn't strange enough, black holes also have a rather gruesome effect on matter known as spaghettification. This phenomenon arises from the extreme tidal forces present near a black hole. Tidal forces are the difference in gravitational pull between 2 points on an object. For example, the moon's gravity exerts a stronger pull on the side of Earth facing it than on the opposite side, causing tides. Near a black hole, tidal forces become incredibly strong due to the steep gravitational gradient. If you were to fall into a black hole feet first, the gravitational pull on your feet would be much stronger than the pull on your head. This difference in gravitational pull would stretch your body out like spaghetti, hence the term spaghettification. As you fell deeper into the black hole, the tidal forces would increase, eventually ripping you apart atom by atom. Section 8. Black holes and light, trapped by gravity. Black holes earn their name because they are invisible to telescopes that detect visible light, the kind our eyes see. Light, despite its incredible speed, cannot escape the gravitational pull of a black hole once it crosses the event horizon. Imagine shining a flashlight towards a black hole. As the light approaches the event horizon, it gets bent by the intense gravity. If the light crosses the event horizon, it cannot escape and falls into the black hole. This bending of light is one of the key predictions of general relativity. It has been observed around massive objects like the Sun, and it provides strong evidence for the existence of black holes. While we cannot see black holes directly, we can detect their presence through their effects on surrounding matter. For example, as gas and dust fall into a black hole, they heat up and emit X-rays, which we can detect with space telescopes. Section 9. Hawking radiation black holes aren't entirely black. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery about black holes. He showed that black holes are not entirely black, but emit a faint radiation due to quantum mechanical effects near the event horizon. This radiation, now known as Hawking radiation, arises from the creation and annihilation of virtual particle pairs near the event horizon. Occasionally, one particle from a pair will fall into the black hole, while the other escapes into space as Hawking radiation. Hawking radiation is incredibly faint, and it has never been directly observed. However, its existence has profound implications for our understanding of black holes. It suggests that black holes are not eternal but slowly evaporate over time. The rate of evaporation is incredibly slow, especially for large black holes. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely. Section 10. Supermassive black holes, the heart of galaxies. While stellar mass black holes form from the collapse of massive stars, there is another type of black hole that dwarfs these in size and mass: supermassive black holes. These behemoths can have millions or even billions of times the mass of our Sun. Supermassive black holes are found at the centers of most, if not all, galaxies, including our own Milky Way. They play a crucial role in the evolution of galaxies, influencing star formation and the dynamics of gas and dust. The origin of supermassive black holes is still a subject of active research. One possibility is that they form from the mergers of smaller black holes over billions of years. Another is that they formed from the collapse of massive gas clouds in the early universe. Regardless of their origin, supermassive black holes are awe-inspiring objects. Their immense gravitational pull shapes the galaxies around them, and their study provides valuable insights into the workings of the universe on the grandest scales. Section 11. Conclusion. The enduring allure of black holes. Black holes continue to captivate our imagination and challenge our understanding of the universe. They are cosmic enigmas where gravity reigns supreme and the laws of physics are pushed to their limits. From the bizarre effects of time dilation and spaghettification to the mysterious nature of the singularity, black holes offer a glimpse into the most extreme environments in the cosmos. Their study has revolutionized our understanding of gravity, space, and time. As we continue to explore the universe, black holes will undoubtedly remain at the forefront of astrophysical research. With each new discovery, we peel back another layer of the mystery, revealing a universe stranger and more wonderful than we ever imagined. The journey into the abyss is far from over.